That's supposed to be at the peak of that. That's not a very good drawing. All right, are y'all seeing this? I graphed in blue the sine curve. Everyone should know sine is bounded between -1 and 1. It's periodic, goes through one full period in 2 pi. It keeps going in this direction, that direction. I just drew one period just to get a basic idea of what's going on. I skipped over the y equals x because there's a little bit of trouble here I'm not quite sure about. So I jumped to these two. Pi over 2, x equals pi over 2, x equals pi. Those are vertical lines. So pi over 2, pi. The question is, where is this y equals x? Like, what does it look like? Because, look, if it looks like this, do y'all see the region or not? Yeah. It's like here, there, all of that up to the line. It would be right in here, right? It is a perfect 45, but you know, is it down like this? No, you know what I'm saying?
It goes,
where would it go?
y equals x is a 1-to-1 ratio, so right there. It'd be at.
Would it be here?
It'd be before.
It'd be before.
It'd be before that, yeah.
So, think of it this way. On this graph, if I plug in pi over 2, what is pi divided by 2? 1 point something? So if I plug in 1 point something into this red function, if I plug in, let's do it this way. If I plug in pi, where should I be? At pi, right? Which is where? 3.14? Way up there? If I plug in pi over 2, where should I be? Pi over 2, which is above 1, isn't it?
Yeah.
So it's like up here somewhere.
Oh, okay.
And then this point's here. So I can pretty much say that it's going to look like that. Do y'all see the region?
Yeah. But that's an easy vertical line.
I think we do verticals here, right? Vertical rectangles?
Yeah.
Vertical rectangles. You do not want to do horizontal rectangles here. Why? You'd have to break it into 3 different things, wouldn't you? Because you would have, you know, if you try and go horizontal, your right and your left are going to switch as you move through this region. Vertical, what's always on top? The red, y equals x, and what's always on the bottom? Sine, right? So we want vertical for sure, right?
I'm sorry, how did you get the y equals x line again?
Okay, so this function right here, this right here, if I tell you to plug in 2 here, what does it spit out? 2, right? If I say plug in 3, what's that 3? What we did is we said, what happens if you plug in pi over 2? It should spit out pi over 2, right? But what's pi divided by 2? It's bigger than 1, right? So here's 1. I didn't want to go 1, I went up a little bit. And all that did was help me see that this line pitches up above this curve point, not below it. All right, vertical rectangles, everyone sold on that? Vertical rectangles. And my integral, do I know where it's going to start and stop? Yeah, I can tell by the drawing, right? It's going to start at pi over 2 and end at pi. And then it's going to be the top function minus the bottom function. What's the top function? X. Minus, what's the bottom function? Sine x. Dx. Whatever that is, that's the area.
Yeah, it looks way worse than
Good? You mean in here?
Yeah.
Because it said between pi over 2. Oh, you're saying because you want to count It's got to be, but it's got to be bounded by all of these. So it's got to include this as a boundary. I understand there could be some question as to whether or not that region, if you want that region.
So on this one, like those lines in there, that's not even one of the things to track. You're actually
Wait, that's not even what?
that's not even one of the things you're like tracking from. You're actually
No, using them for the limits of integration. Is that what you're talking about? These right here? Yeah, those give me my limits of integration. Yes.
So to understand the logic of this better, so because those other two are like in there, the pi over 2, well, yeah, we'll just say the x equals pi over 2. So because that's within, the start of y, go ahead and word this. So y equals x to pi. It's that big old triangle that encompasses all 4 of those functions.
Mhm.
So rather than like even caring about, from the first function to the second function, you can just like fast forward and go from first to the last with the total area. I don't know if that made sense. So like, in other words, you wouldn't have to do the process of, finding the integral from y equals x to pi over 2, and then from pi over 2 to pi.
Yeah, I think this is kind of like what the question Nathan was asking, which was, like, why are we not doing this region? The implication in the wording is to sketch the region bounded by all of those, and this region right here would only be bounded by 3 of them and not all 4. Like this region right here is bounded by the sine, the pi over 2, the y equals x, and the pi. All 4 regions bound that. The region is bounded by all 4 of those curves, as opposed to this one, which is only bounded by 3 of the 4. That's why I'm not caring about what's happening in here.
So on our homework questions, it's gonna are some of them gonna be to where we just
Yeah.
Okay.
Yeah, you always get to choose now if you're going to do function of x or function of y. Yes?
So for this, because you said in the future, it will get more complex, but that's outside the bounds of this class. So for this class, we're gonna have to sketch, using our knowledge, we have to sketch the graph to see which ones we're gonna use, and
Yeah.
instead of finding it somehow algebraically or something.
Yeah, you're going to need to have a decent idea of what these graphs look like, which is why I said bring your graphing calculators, because you want to have that tool. I do want a good picture. If you have to find intersections, I want you to find them algebraically, unless I tell you otherwise. This is maybe not as easy for people to know what the graphs of these look like. Right, so you might want something, but there's also a bigger problem, and that is both of these, two of these curves up here, right, this one and this one, are solved for x, aren't they? Which means that they are given to us as functions of y already, because they're all solved for x already. So if it's solved for y, if you see y equals something with x's, those are functions of x. If you see x equals and then a bunch of y stuff, then those are functions of y. So we have 2 functions of y, and then we have this other restriction that y must be greater than or equal to 0.
So it already tells you you're going to be horizontal, basically.
It's kind of leaning that way. I need to draw it first, because if I needed to, I could solve this for y. I could take the 4th root on both sides, and then over here I could square both sides and get y, but I'm hoping I don't have to do that. Yes?
It's probably not safe to assume that you can usually assume that, right? Like if it's given to you in that term, then it's going to be horizontal, or is
It's probably going to be horizontal.
probably?
Probably, yeah, but you should always be open to the idea that you could switch. Sometimes you'll get one where one of the equations is solved for x and the other one's solved for y. So then you have to figure out which way am I going to go here.
Either way is generally always a good idea to just graph it.
Graph it, and then that'll usually indicate which way you want to go.
So in our calculator, how does it solve for?
It doesn't. Your calculator can only graph functions of x. It can't graph functions of y.
So if we wanted to use the calculator, we have to solve it x. Or solve
Yes, kind of.
It's not that hard.
but I have an even better option for you. So let's see if we can do this without a calculator, though. All right, let's just see if we can. It's not as bad as it may appear to be. All right. If this was the other way around, if it was that way instead, do you know what that looks like? Kind of like a parabola, but just a little bit sharper, grows faster, right? So this is basically a parabola, but it's not going up, it's sideways because it's x equals y squared, right? So again, without getting ourselves like too intimidated by it, x equals y squared, or y to the fourth, I said y squared. X equals y to the fourth. It should look like this. And this is a rough sketch, okay? But it's kind of parabolic. In reality, it's probably more like this. Like it's very close and then it just jumps like this. That's probably not that good either, but either way, it's kind of parabolic looking to the right, all right? Okay, now, the other one's a little harder. The other one's a little harder. So maybe I can do the same analogy. Would you know how to graph this? Maybe? Do you know what a square root looks like? Square root function. It's either going to look like that, or it's going to look like that, and then maybe it would be flipped over, who knows. In this case, there's no negative in front. So it's either going to look like this, or it's going to look like this. Let me see, let me rearrange it. Negative x plus 2, let's see. Just plug some values in.
Well,
How could you get 0 under here?
the values have to be greater than total or zero.
How do you get 0 underneath here? What do you plug in? Negative 2? Yeah, positive 2, sorry. I misread the problem. Positive 2, you get 0, right? Okay, what else can you plug in here? Can you plug in 3? Can't plug in 3. Plug in 3, you get negative 3 plus, it's negative under the root, can't do it, right? So you could plug in 1, right? 1 would work, and you could plug in 0. So this thing goes like this, doesn't it?
Oh, yeah. That makes sense.
That makes sense?
Yeah.
If you plug in 2, you get 0. You can't plug in 3 or you'll get negatives under the root. If you plug in 1, you get negative 1 plus 2 is 1, square root of 1 is 1. If you plug in 0, you get square root of 2, which is bigger. Right? So I said it had to be this or this because it's a square root. And so it's got to be that one, right? Now that's what it would look like. That's what it would look like if it were this, right? This is the x-axis, this is the y-axis. So ours is reversed, right? Ours is actually like this is y and this is x, right? That's kind of what we should see here. So what's that going to look like then? Our y-axis is what? Positive 2, which is up here, right? And then which way does it go? Which way is that arc going towards?
Towards negative.
Negative y values. So like that. Right, this is your y. We're switching our x and y. So the y values start at positive 2 and then they go negative. The y value starts at positive 2 and then they go towards negatives. The x values are positive. The x values are positive. That is x equals the square root of 2 minus y. Do y'all see the region yet or no? We have one more condition, don't we, that I haven't put up here? That one right there. Y is greater than or equals 0. Y is greater than or equals 0 means up here like this, right? So above the x-axis. There's only one region that's enclosed by both curves and everything above the x-axis, and that's right in there. Do y'all see that this would flood out this way, right? That would flood out, that would flood out. So that's the only thing that's contained by the x-axis. Okay, what do we want to use here, vertical or horizontal? Horizontal for sure, right? We don't want to switch it. We have a function on the right, function on the left that never changes, right? So I can say right now, I know the integral setup. It's going to be, which function is on the right? Square root of 2 minus y. Okay, and then I subtract from that, what? The y to the fourth, which is the blue function on the left, dy. See, that I already know because of where this curve and that curve came from, right? The only thing left is my limits of integration. Where am I going to start and stop? And because it's horizontal, I'm going from, y values. So I start where? 0, and I stop? Not sure yet, right? I need to figure out where they hit each other. Not at 2 though, right? Because 2 is further up. I need to know where they hit each other. So I have to set them equal to one another, right? I have to set them equal to one another. So I set root, this is my intersection here. I set 2 minus y equal to y to the fourth. Now that is not an easy equation to solve. You can try it. Square both sides. You get 2 minus y equals y to the eighth, right? Because when you square y to the fourth, you double that power.
Why are we solving the equation again?
To try and figure out where they intersect one another so I can get this y value to get my upper limit of integration. That is not a quadratic though, right? This looks like y to the eighth plus y minus 2 equals 0. Just move everything to the right-hand side. And then that's not a quadratic, right? And we don't have a clean method for this, right? We don't have a clean method. So this is one of those problems that can appear like in your homework where you're like, well, crap, I don't know how to solve this. What the author is expecting for you to do is just try and think about what the answer would be. Like there's an easy answer. It's 1. Just do a visual inspection. 2 minus 1 is 1, square root of 1 is 1, and then 1 to the fourth power is 1. So this is a solution by inspection. I'm not quite sure how else you get that. I mean, well, I don't know how else they expect you to get that. We could use, there's other methods, but Newton's method and yeah.
So is the thought process like there's no way I'd be able to solve this? Would I know? So you just try to do it?
There might be a way to solve that. It's just it's not a common way.
I mean, you could also just always plug it into the calculator, but that's no fun.
Okay, so do y'all want to see how I would solve that?
Yeah.
If I didn't, like it's not a quadratic, right? I would do something from college algebra called the rational zero test. And the way the rational zero test works is that if you have a polynomial and you want to try and factor it or break it down, find any of its zeros, what you do is you use synthetic division. So you draw this upside down box and then you put all the coefficients of the polynomial in here. So I have 1 in front of y to the eighth. What do I have in front of y to the seventh?
0.
Nothing. Sixth?
0.
Fifth power? Fourth?
0.
Third? Second? First? 1. Constant? -2. So I'd do this, and then what I would do is I'd start trying things that would potentially get me a 0 at the end of synthetic division. And if you go back and look at the way you do it, is you take the number in the back, -2, you take the number in the front, +1. You list out all the factors of -2, which are ±1 and ±2. Then you take all the factors of 1, which are ±1. Then you create this list by taking all of these and dividing by all of those. Does that look at all or sound at all familiar to something? It's called the rational zero test, college algebra. And then you start trying each of these with synthetic division. And if I did that and I got to this, -1, which is in this list, I would do my synthetic division. 1 would come down, multiply, I get -1, and then add down -1, then I get 1, then add down, then get -1, then down, and then 1, and then down, and then -1, and then down, and then 1, and then down, and then -1. Shit, no. -1, hold on. 0, hold on, I messed up. Where did I mess up? 1. 1. This should be working. Do I have enough zeros there? 0. No, something's wrong. Y to the 8. Because we got a solution, right? What's our solution? 1?
Shouldn't the first one be -1? Oh, wait, never mind.
So this is the 8th power, 7th, 6th, 5th, 4th, 3rd, 2nd, x, -2.
So move it up over 1 0.
Well, it's supposed to be.
Oh, it's that, okay, I see it. I think I see it.
What?
On the third 0, that should be a positive one.
Where here?
The third 0. The third 0. The next one over. Yeah, on the bottom.
You're adding down.
Oh, wait, you're right.
Right, so 1,
Why
-1,
did you move, 1 on the outside in the first place?
1.
That second row, do you move everything over by 1?
Mm-mm. This first one comes down. This just drops. Then you multiply. -1, add down. Multiply, put it here, add down. Multiply, put it here, add down. Multiply here, add down. Multiply here, add down. Zero. See, we should be getting, at the end here, we should be getting 0.
Yeah.
That tells us that x plus 1 is a factor. What was our answer?
1. Yeah, you chose y equals 1.
Ah! What happens if we use 1? It'll be 0. That's my problem. I picked the wrong starting place. 1. I thought our answer for some reason was -1. I wasn't thinking. Sorry. 1. Let's see. 1. If we do that, then what happens? 1, 1, 1, 1, 1, 1. Right? 1, 1, 1, 1. 1, 1, 1, 1, 2, 2, 0. So we get a 0 at the end, which tells us that 1 is a solution to, that tells us that 1 is a 0 of the function.
Well, how did we get the 1 in the first place?
That's synthetic division. You mean, where do we get this?
Yeah.
From this list of numbers. I'm just telling you, the big thing here is that there's a way to try to solve polynomial equations when the degree is higher than 2, right? There's a method you can try. Now, this doesn't always work because the rational zero test relies or requires that your zeros are rational numbers. If you have an irrational 0, then the test won't work. Like, what do I mean? If, let's say you take this right here. Let's say you wanted to solve this. Okay? Then you try synthetic division. So you set this up, you go 1, 0, -2. And then you start trying to use numbers to figure out what will make this final thing 0. If you do it, never going to happen. Because the only two solutions to that are positive root 2 and negative root 2. And square root of 2 is an irrational number. So the rational 0 test only works for rational zeros. So there's limitations to it, which is why Newton's method, which is a Cal 1 method, is even better. Yeah?
Does y being, if this said y is greater than 0 instead of greater than or equal to, does that change anything?
We could still, because one sliver line has no area, but that won't ever happen. I mean, it doesn't make sense to ask that question without including the boundary.
Yeah. So
Yeah.
will that ever matter if we're taking the area of 0 to?
Will it ever matter? No, because the boundary will always be given. There will always be a boundary there. Now, you're getting into another territory because that is a question we ask later. I was actually talking to my Cal 3 class about this the other day. Have y'all ever heard of Ted Kaczynski?
Yes.
Y'all know who I'm talking about?
Yeah.
You know, who is he?
Unabomber?
Unabomber.
Yes,
The
yes.
Unabomber. Do y'all know that he was a mathematician?
Yeah.
Yeah.
And he was studying boundary value problems, which is, it drives you crazy, I guess, I don't know. But you know what I'm saying? Like we avoid some more difficult questions about what happens on boundaries when they're not included. So we're getting closer and closer to the boundary without actually getting there, and like how do things behave? That's a different sort of animal that we don't address in here.
I was thinking like maybe you just put like minus dy at the end or something like that.
Yeah, no, it just becomes, yeah, it's something that we'd look at, just not yet.
So we do have a problem, we're gonna wanna blow someone up.
I'm not sure what you'll do. Go live in the woods somewhere. Okay, we don't have enough time for another problem right now. Let's just look at this. Now this next one is pretty straightforward. You have two functions here. They're both functions of x. X is greater than or equal to 0. So if you were doing that, that would probably be vertical, right? Rectangles.
Are we going to 3D next class, or?
We will go, yes, but not, yes, we are. We're going into 3D next time. I have 5 minutes. I'm trying to decide what I want to do in 5 minutes. What's more important to you? What's more important to you is I can tell you how to use your calculator to graph a function of y, not a function, like, it can only do a function of x. Let me show you how to do it as a function of y. All right? So this is going to work for pretty much everyone here has a TI, if you have something other than a TI. So when we graph, I've only got 4 minutes. When we graph something like this, everyone here knows how to graph this on their calculator, right? Okay. So if you don't, that's another day, not right now. I want you to go to your calculator, go to your mode, and then in there you're going to find for graphing, I don't know, it's either going to say like func. I think it says func, just func. And then there's one that says para. Do y'all see this is under the graphing?
Yeah.
Yes? It's like func, para, pole, and sequence, right? Right? Okay, right now the standard default setting is func, which means that your calculator is going to be looking for functions of x. We are going to switch into what's called parametric. So switch to parametric on your calculator, and then go back to the same place you would go if you were going to type in a function. I think it's the y equals button. Okay? All right? It's going to look different now. What it's going to have, I believe, is something like this. xt1 or something like that, and then yt1.
Yeah. The order of the t's and ones is different.
Okay, so it's x1t?
Yeah.
Okay, x1t, something like that. And then y1t, and then the next one is x2t, y2t. Yeah?
Yeah.
Okay, let me explain what's going on here. Back in the good old days of functions, if I were to look at this as a graph, right? You have the x coordinate gets plugged in, and then in this particular case, it's x squared, right? So if you look at it as an ordered pair, the x coordinate is the x that got plugged in, and the y coordinate is that x coordinate squared. That's what would be happening here, right? The x value is x, the y value is that x being squared. What we're going to do with parametric is we are no longer going to let x be the thing that's being plugged in. What's going to be plugged in is t, which is some variable in the background that we never get to see. It's like a clock in the background. So I'd like for you on x of t, I want you to put in t. Now your x variable button should also have the t on there. No? Do y'all see it? Your x variable button should also work as a t button.
Where is the x variable under mode?
And then on the y1 of t, I want y'all to put t squared. and then I want you to hit graph, and I want you to tell me what it does. It drew half the parabola, didn't it?
It actually didn't draw anything for me.
Okay, I'll come back to you in a minute. All right, so you got half the parabola. That is because by default, your calculator is only going from t equals 0 to 2 pi. That's just because it assumes t is going to be like an angle. So you should have the option to change what's called your window. I think it's window. Window, and there should be a t min, t max. Are y'all seeing that? T min, t max. Change your t min to -10 and change your t max to 10. And then graph it again. And you'll get the whole parabola. Okay? Now, let's draw this. X equals y squared. This is actually a parabola that it's sideways. Okay? So the way we want to think about this is that it's the opposite of what's happening here. It's not t squared, it's t squared t. It's the reverse. So put t squared here, t, and then when you do that, you're going to draw your parabola sideways. It'll draw the parabola sideways. Did you do it?
Yeah.
Okay, one more, and then we'll go. So let's go to